Hello everyone. So in the previous video we have discussed the property of linearity and time shifting, and we were discussing the properties of continuous time Fourier transform. In this video we will discuss about conjugation and conjugate symmetry property. So what this property states, so the property states that suppose xt is having a Fourier transform which is represented as x of j omega, then if we will take the conjugate of xt, so x conjugate t will have an equivalent Fourier transform represented as x conjugate minus of j omega. So this is the property of conjugate symmetry. So we will try to derive this property in a very short. So suppose we have the formula of x of j omega, which is the integration minus infinity to infinity x of t e raised to the power minus j omega t dt. And now what we'll do, we'll take the conjugate on both sides. So here on LHS we have taken a conjugate, this is also the conjugate. So what will be the output? Output will be minus infinity to infinity x conjugate t e raised to the power, now it will be plus j omega t dt. Now what we'll do, we'll replace omega with minus of omega, and what will be the output? Output will be x star of minus j omega will equal to minus infinity to infinity x star t e raised to the power minus j omega t dt. So from the property what we have seen, if xt is the signal, then x of j omega is the Fourier transform, and if x star is the signal, then the output will be x star of minus j omega, and that was the property which we have stated. So this is the property of conjugation. And now there are some small points which is very useful, which is related to this property. So suppose xt is real. So if xt is real, then what will happen? X of t should be equal to x star of t. And what this implies, that if we'll put the equation number 2 in this previous equations, so what we will get? We will get x of j omega as x conjugate of minus j omega. So this is a small inference of that property. Now we can have a quick example for this also. Suppose we have xt, which is denoted by e raised to the power minus at ut. So we have already derived the Fourier transform of this function, that is 1 by a plus j omega. And now if we'll replace x of j omega with x of minus j omega, what will happen? It will give us the form of a minus j omega, and which is equivalent to the conjugate of j omega. So suppose we have x of j omega, and if we'll do the x conjugate of j omega, what will be the output? Output will be 1 by a minus j omega. So x conjugate is equivalent to x of minus j when xt is a real function. So it is just a small example to understand this statement. So now we'll move on to some other points which can be extracted from this property. So suppose if we express x of j omega, that is the Fourier transform of our xt. So x of j omega is your Fourier transform of xt function, and if we express this x of j omega in rectangular form as, so x of j omega is represented in rectangular form as real part of x of j omega plus j times of imaginary part of x of j omega. So this is the rectangular part of this x of j omega, that is the Fourier transform of xt. And now we are saying that xt is real. So if xt is real, then what will happen? We will get real part of x of j omega is equals to real part of x of minus j omega, and imaginary part of x of j omega will be equal to minus of imaginary of part of x of minus j omega. So this can be directly inferred from the previous statement. So what is the output of this expression? That we know that this is the even function and this will be your odd function. So when we represent a Fourier transform in rectangular form, the real part will be an even function and the imaginary part will be an odd function. So now if we say that, so in the next point what we say, that xt is both real and even. So in that case, the Fourier transform, that is x of j omega, will also be real and even. This can also be derived using a small derivation, that suppose we write x of minus j omega, that will be equal to minus infinity to infinity xt e raised to the power j omega t dt. We are just replacing x of j omega as x of minus j omega in case of the Fourier transform equation. Now we will replace tau, which is equivalent to minus t. So x of minus j omega will be equal to minus infinity to infinity x of minus tau e raised to the power minus j omega tau d tau. And we are saying that our xt is even function. So x of tau will be equal to x of minus tau. If we will replace this here, so what will be the output? The output will be x of minus j omega should be equal to minus infinity to infinity x of tau e raised to the power minus j omega tau d tau, and this is very familiar form. So this is the x of j omega. So you can see x of minus j omega is equivalent to x of j omega. So that is, it will be an even function. So if your xt is real and even, x of j omega is also real and even. And similarly you can derive, and I'll just write here, if xt is real and odd, then your x of j omega will be purely imaginary and odd. So this can be easily derived using the previous derivation. So now there is another form, like any signal can be represented in form of its even part and odd part. So here xt is signal and xc represents the even part and x naught represent the odd part. So any signal can be represented in this form. And also if we will see that using the linear property, if we will take the Fourier transform of x of t, then it is equivalent to Fourier transform of x e t, that is the even part Fourier transform plus Fourier transform of the odd part. So what this infers, suppose we have x t as a signal and x j omega represents its Fourier transform. So what we will get, the even part of x t has a Fourier transform which is equivalent to real part of x of j omega. And what will be the odd part? Odd part Fourier transform will be equal to j times imaginary part of x of j omega. So these are the two properties which can be inferred from this statement, that we are splitting our signal in two forms, that is, one is in even part and odd part, and we are taking Fourier transform of individual even and individually odd part. So the even part Fourier transform will be equal to the real part of x of j omega, and odd part Fourier transform will be equal to j times imaginary part of x of j omega. Now if you are not able to understand this property, we will take an example to make it more clear. So we can use this property and try to get an Fourier transform of a signal which we already discussed, which is e raised power a mod t. So from our previous discussion, we know that the Fourier transform of this signal is 2a by a square plus omega square. Now we'll try to get the Fourier transform of this equation, not using the direct formula. We will use this conjugation property and then we try to derive it. So how we can do that? We know that we'll pick a signal that is e raised power minus at ut, and we know the Fourier transform of this signal which is equals to a plus j omega. Now xt is your e raised to the power a mod t, which can be written as e raised power minus at u of t plus e raised power at u of minus t. How we are writing this? The function is basically following e raised power at when t is less than 0, and it is following e raised power minus at when t is greater than 0. So this part is represented by this graph, and this part is represented by this graph, and this is summation of these two parts. So now we can also write this function as 2 into e raised to the power minus at ut plus e raised to power at u of minus t divided by 2. And suppose we have an function xt which is written as x of et plus x of ot, and these are the even part and odd part. So this is your x of ot. So now x of et can be written as 1 by 2 of x of t plus x of minus t by 2. You can directly replace x by x of minus t and just add, and you will get this. So this will be this can be only 1 by 2, this is redundant. So this is just 1 by 2 xt plus x of minus t. So here this is the same form. So you can see that if your xt is e raised to the power minus at ut, then x of minus t is represented by this. So how we can write it? We can write this form as so xt will be equal to 2 times of even part of e raised to power minus at u of t. So you understood, like we have this function, so the even part of this function can be represented by this, and this is the form for our x of t, that is equals to e raised to the power minus a mod t. So and we also derived that even part of a signal Fourier transform is represented by real part of x of j omega. So our signal is now this e raised to power minus at ut, and we know the Fourier transform of e raised to power minus at ut as 1 upon 1 plus a j omega. So if we will take the real part of this signal, we can directly get our Fourier transform of this signal. So e raised to the power minus a mod t. So what will be the Fourier transform? That will be equal to 2 times real part of 1 plus a plus j omega. So just multiply this with the conjugate. So we will get 1 plus j omega multiplied with 1 minus j omega, a minus j omega, real part of this. So this will be equal to 2 times real part of a by a square plus omega square minus of j omega by a square plus omega square. That will be equal to, the real part will be equal to 2 times a square plus omega square. So and you can see that this result is equivalent to this result which we have got from the formula and which we have derived in our previous case. So this is the form. So this equation and this equation are same. So in this manner we got the Fourier transform of e raised to power a mod t using the conjugation and conjugate symmetry property.